In this section, we're going to work out how we calculate vector fields like electric fields, magnetic fields, gravitational fields from realistic distributions of charge, current, mass, whatever it might be that's causing the field. We saw before that if you use the fundamental equations like Gauss's law or Ampere's law, that can allow you to work out very quickly what electric, magnetic, etc. fields are in very simple symmetrical cases like spheres in infinite sheets of charge, infinitely long solenoids, and so on. However, these are not generally very realistic situations. Most solenoids are not actually infinitely in length. A capacitor is made of sheets of charge, but they're not infinite sheets of charge. So what we're going to talk about now is how we work out the fields in situations where things are not infinite and symmetrical. And as you will see, the methods are very much like what we've been talking about so far, numerical, step equations, calculus, and so on. Start off with a case study of a rod. Let's say it's a plastic rod. It's got length L. Let's say we've rubbed it with a woolen glove or something like that, so it's acquired a static charge. And we'll assume it's got some charge Q, which is spread uniformly up and down the rod. What's the electric field caused by this? Now the first step is always to think about the physics. Now if it's got a positive charge, that means we're going to have field lines going away from it. In some sense like this. But the exact shape is going to be a bit tricky. However, you can estimate what's going on in two limiting cases. One limiting case would be to zoom way out. Let's say our cylinders, we now look at it from a long distance, so it looks something like that. And we're trying to measure the fields out here or here or here. Now in this case, the fact that it's a rod of length L kind of doesn't matter. You can approximate it as just being a point at the same location, and that will give you very much the same answer. In which case the electric field is given by Coulomb's law, which is 1 over 4 pi epsilon naught mod r squared, and it points in the direction r. So if this is r, which is the vector from the charge, say in this case, say the middle of the rod, to where you're measuring it, then you add an r hat here to make sure it points in the right direction. So when you're a long way out, you expect the electric field to go as 1 over 4 pi epsilon naught distance squared and point radially outwards. How about if you're very close in? So let's say you're somewhere like here. In this case, you could probably approximate the whole cylinder as going on forever. The fact that it ends doesn't really matter because where it ends is a long way from where you are. In this case, you can use Gauss's law. If you remember, Gauss's law says that the surface integral over any surface of the flux of electric field, it's electric field times the normal vector dA, is equal to the charge inside that surface divided by a constant. So in this case, if we pick a location very close to the centre here, we can pick a Gaussian surface. That's a cylinder. And we can use Gauss's law. Now what's the charge inside the cylinder? That's going to be the charge in this little bit here of the rod. Let's call our Gaussian surface height delta x, let's say. Now, as the charge is spread uniformly up and down the entire rod, if the cylinder is 1% of the rod, it'll have 1% of the charge. So the charge inside, it's delta Q if you like, so delta Q is going to be equal to the fraction, which is delta x over the total length times the total charge. So if delta x is 1% of the total length, delta x over L is 0.01 times charge. And that's got to be equal to the surface integral over the surface. Now if we're a long way from the end, it's telling us the electric field is going to be pointing pretty much straight outwards in all directions. which means the surface integral over the top and bottom is going to be 0 because the electric field is parallel to the surface, it's not crossing it. All that matters is the surface integral around the outer surface, and that's just going to be equal to the strength of the electric field times the area, which is 2 pi r delta x. So from that, we find that the delta x's cancel, and we get that the electric field, strength of the electric field, equals Q over L, so charge per unit length, over 2 pi, in this case mod r. So we've got two limiting cases. When you're a long way out, the electric field depends on the total charge. There should be a Q up there. Constant 1 over 4 pi epsilon naught, and goes down as inverse square, so this distance squared. When you're close, it depends not on the total charge, but on the charge per unit length, and instead of going down as r squared, it only goes down as r. Okay, so that's our limiting case. However, in reality, we're going to have something a bit more complicated. We're going to have an electric field that goes straight out here. In the distance, it's going to be pointing away from the center, and there's going to be some intermediate stage where it goes somewhere in between. Let's see how we calculate that.